everyone. Just heads up, we're going to get started here in just a few minutes for the next oral session. So if you're outside, please come back, take your seats. We'll see you in a minute.
Amazing. And we have to use the mics, right?
Yeah, of course.
Yo.
Do you want to just go on stage and?
Yes. You're the first speaker? Perfect.
Yeah. Wait.
Sorry.
Hello. Are you one of our speakers? Yeah, I'm the second speaker.
Oh, you're Jen. Okay, Jen.
That's Jed. We're looking for Wei Sun. Do you know Wei Sun? I hope that he will. Okay. We have 4 of the 6 here. This is good.
And I think the last one, Joey is using.
Joey, I don't see, no.
He's from Stanford, so I see.
He's always late. Stanford people are always late.
No, Berkeley too.
I've heard this before. So we should try to stay on time, if that's okay.
Should I go into these?
Yes, and then just if no one, if they're not here, just make a announcement.
Perfect.
It's getting better.
Hello.
Just double checking Wei Ray.
Yeah, we're
Perfect.
Thank you.
All right. Hello, everyone. Hello, hello, hello. Welcome to our 6th oral session. We're really excited to have you all here. I'm Nima, that's Shiran, and we are your session chairs. We're going to get started. Our first speaker is Wei Ray. He's going to talk about his work on reinforcement learning with foundation priors. If we can have his slides. Perfect.
Yeah. Okay. Hello, everyone. I'm Wei Rui Ye, a PhD student at Tsinghua University. Today, I'm very glad to share our work, reinforcement learning with foundation priors, let the embodied agent efficiently learn on its own. As we know, reinforcement learning is a great tool to learn policies for robots. However, current RL algorithms have 2 primary challenges: heavy reward engineering and sample inefficient. Here we take an example of the pressing button task on Meta World and demonstrate how the vanilla reinforcement learning works. Under the human-designed reward function, the robot arm starts to try and error by exploration. For the first 1,000 frames or even 10,000 frames, the agent is still exploring randomly. After 100,000 frames, it can learn to move towards the button instead of moving away from it. After 1 million frames, it finally reaches the button easily and presses it down. So even if humans design a very decent reward function, the agent still wastes lots of time and exploration in meaningless states. And this is not what we want. So let's see how a baby makes it, which is a common example in psychology for the pressing button task. Here, the baby named Alice tries to move towards the button and adjust the position to touch until she finds some part that can be pressed down. This is amazing because the baby never presses the button before. So the reason she can make it is that humans solve tasks under the common sense prior knowledge accumulated in daily life. They will not spend time in random exploration. Instead, they will start from reasonable behaviors to explore, make adjustments, and reinforce the successful behaviors. So when the button is in front of you, you just stretch out your hand and move towards it. So can we try an error under the common sense knowledge for the embodied agents? Luckily, the answer is yes. We have access to amounts of foundation models which are trained on the internet scale data set. And they are full of common sense knowledge. So that's what we want to do, the foundation reinforcement learning. Then 2 questions come out. For the first, what is the concrete form to present the prior knowledge for reinforcement learning? For the second, once we have those prior knowledge, how to leverage the prior knowledge for downstream tasks? So in this work, we try to figure out the two questions. So going back to the button example, let's analyze the baby's behavior systematically. During the learning process, Alice will ask her about 3 questions. What should I do? She knows the rough behavior, namely moving towards the button and press it down. So this is the policy prior knowledge. Am I closer to the goal? She can make adjustments to find some part that can be pressed down, and she knows it's better if she can move towards the button. So this is the value prior knowledge. Do I succeed? When the button lights up, and she can realize that she makes it, and she will reinforce the successful behavior next time to make it better. So this is the success prior knowledge. And we find the 3 priors can be aligned well with the key concepts in the MDP, namely the policy function, the value function, and the success reward function. So we propose to do reinforcement learning under the 3 foundation priors. Afterwards, we need to figure out how to leverage the 3 priors in reinforcement learning. Here we give an example of how to use them in actor critic algorithm. We named it as the foundation guided actor critic. So here, the policy prior will provide actions for the actor, and we do policy regularization in a basic term to regularize the actor. For the value prior, we find it will result in catastrophic forgetting issue if we fine-tune the critic directly. So we choose the reward shaping technique. For the success prior, it gives the sparse 0-1 success reward, and we assume the success reward prior is relatively precise and accurate because of the simplicity of the binary classification for determining the success state. So the auto reward function is formulated as the success reward function, as the success reward plus the shaping reward. Specifically, notice that the value foundation model only depends on the state, so it becomes a potential-based function, which shares the optimal solutions. So frankly, it means that the optimal policy to solve the reward function on the right or on the left MDP is also the optimal policy to the right sparse reward MDP. So it's a good property for optimization. So back to the pressing button task, FAC can solve it very fast in 100,000 frames, which only costs 1 hour training. Instead, the vanilla reinforcement learning with manual design reward cannot make it and still stuck in poor exploration under the same training time. Afterwards, we turn to reinforcement learning on real-world robots during 1 hour real-time training. We choose the code policy as the policy prior, which gives the idea of how to do the task. And thanks to the Thomas talk the day before yesterday, I think most of people here know what the policy prior is. So let's see the policy prior, although it fails, but it can try to pick up the kettle and rotate to water the plants. After 10 minutes training, the agent can learn to pick up the kettle, but it cannot make it firmly so that it drops down. After 20 minutes training, the agent can hold the kettle firmly and stably in the air, but it just makes no success. After 1 hour training, the agent can water the plants finally and in a better manner. And we are not limited in one task. Instead, we conduct experiments on 5 hard tasks on real robots. For the articulated task open door, although the policy fails, but it tells the agent to reach the handle and move back to open the door. So after sometimes training, the agent can learn to try back and forth to grasp the handle, and finally move back to open the door. And also for another task like dynamic task, playing golf, the policy prior fails, but it tells the agent to move back to the ball and make a strike. So after sometimes training, the agent can make better adjustments and for the orientations and the positions to make a better strike. Overall, in 1 hour training, our FAC achieves 86% success rate, while the vanilla reinforcement learning fails in all tasks. And the prior policy has only 22% success rate. To sum up, our framework is sample efficient, minimal and effective reward engineering. Finally, it is also agnostic to foundation model forms and robust to noisy priors. We have detailed ablation studies towards the different qualities of the policy priors in our work. And I hope people here can take away two conclusions in our work. When you do reinforcement learning for real robots, you can try to utilize the policy value success prior, and you can also try the foundation guided critic, use the policy prior to guide the agent and build reward function based on shaping rewards and the sparse success rewards. And we believe real-world RL is important, and I hope our framework can enable future robots to efficiently explore and autonomously learn in the physical world. Thank you for your listening, and welcome for the discussion at the poster 64 afternoon. Thank you.
We have time for 2 questions.
Thank you.
Okay, maybe I will start with the first one. So have you looked at the different kinds of priors you can get? I suppose different VLMs will give you different kinds of priors, different LLMs will give you different kind of priors. Which ones do you feel are going to be the most productive for using as foundations?
I think for convenience, the current vision language model is a good one, especially when you try to design some like code policies or something like that, they can work really well. And for another prior policy we try is the diffusion-based policy. You use the pre-trained diffusion model to generate the videos, and you can use inverse dynamics to infer the action. So that can be directionally good, but maybe it's noisy, but it's fine because the policy prior only tells you how to make it. Yeah. Thank you.
Awesome. I'm not seeing any other questions. Great. Thank you very much.
Cool. Okay, so next we'll move on to our second talk in this session. So that will be given by Ruoxuan Feng, Play to Score. Take it away.
Hi, I'm Ruoxuan from Renmin University of China. And today I'm going to introduce our work about the stage-guided dynamic multisensory fusion for robotic manipulation. Before we dive into our paper, let's take a moment to picture the process of pouring half a glass of water from a bottle without directly seeing the water level. To achieve this, we need to visually align the bottle and the glass, and then decide when to stop pouring based on the sound of the water and the weight change we feel with our fingers. It is clear that even a simple multisensory manipulation task like this can be divided into several task stages, each with its own sub-goal. We use different sub-goals. We use different senses as different stages to achieve the different sub-goals. We summarize this phenomena as modality temporality. We experience modality temporality in our labs every day, and this seems pretty ordinary. But what we want to argue is that modality temporality is actually a crucial aspect of multisensory manipulation that often gets overlooked. It's hard to appreciate this challenge because our humans are so capable and talented of flexibly using all the senses. So inspired by human perception, to endow robots with this capability as well, we've started seeing the emergence of some multisensory robots. And we also built our own multisensory robot system with visual, audio, and tactile sensors. We customized the fingertips to hold the GeoSci Mini tactile sensor. However, when we actually try to use imitation learning to train models for these multisensory manipulation tasks, we found that for robots, dealing with the challenge of modality temporality is not as easy as for humans. In a complex manipulation task, the importance of various unimodal features could change over stages. For example, when pouring water, only the visual features are required for alignment, while the audio and tactile features provide no useful information. In the later stages, the audio and tactile features become crucial, while the visual features become less important. There can also be some smaller changes within a stage, like the sound might kick in halfway at the start pouring stage. We categorize them as cross-grain and fine-grain modality importance change. These changes in modality importance put high demands on multisensory fusion algorithms, as they need to dynamically focus on the modalities as needed. So to better tackle the challenge of modality temporality, we want to enable the model to understand the task stages and perform dynamic multisensory fusion accordingly. So we mainly focus on two key issues: how to achieve task stage comprehension and how to use stage information to guide dynamic multisensory fusion. For the first question, a simple and effective approach is to train the model directly to predict the current task stage. To achieve this, we first label the stages for all the training samples. This process can be done both manually or automatically using the large language models. We found that as long as a suitable prompt for task description is provided, the large language models can effectively label the task stages for each training sample in the trajectories. We then use a gate network to predict the current task stage by weighting a set of learnable stage tokens. We use the stage labels to penalize the stage prediction scores. Then, we inject the stage information into the state token, achieving a cross-defined task stage comprehension. Based on the state token infused with the stage information, we can perform stage-guided dynamic multi-fusion now. We use the new state token as query and dynamically focus on the modalities needed for the current task stage through cross-attention. The final action prediction is made using the fused feature. Together, we introduce our MSBot, a stage-guided dynamic multisensory fusion framework. We encode the multisensory features and the action history into a state token. And the integrated dynamic fusion and stage comprehension modules allow us to dynamically allocate the weights of the modalities based on the task stages. We evaluate our method and the baselines in two challenging multisensory manipulation tasks: fine-grained pouring and the pack insertion with keyway. In the pouring task, the robot arm needs to pour out a target mass of small beads. For the pack insertion with keyway task, the robot needs to rotate and insert the pack to align the key with the keyway on the base. You can think of it as a simplified version of turning a key. Both tasks require 3 modalities to complete. Thanks to the stage comprehension, our method outperforms the baselines that use simple concatenation, LSTM fusion, and self-attention fusion in both tasks. You can also see how MSBot effectively works in this demo. Thanks to the accurate stage comprehension, the attention scores in MSBot show clear stage characteristics, which matches the way we think as humans. Also, when we remove the stage and state guidance from the dynamic fusion, we can see a performance drop in the task. We also want to see if our method could handle different visual distractors. So we change the color of the cylinder and the base, and we also place some clutter around the base in the pack insertion task. As you can see, our method is minimally effective because dynamically adjusting modality weights helps reduce the impacts of distractions on the fused features. So to sum it up, we have highlighted the challenge of modality temporality in multisensory robotic manipulation and proposed a stage-guided dynamic multisensory fusion framework to handle it. This leads to more effective and explainable performance in real-world tasks. For more details, demo, and code, you can visit the website or scan the QR code. You can also come to our poster, and I'm very happy to answer any questions. Thank you.
Okay, any questions from the audience? Maybe Sunny?
Hello, thank you for a great talk, very interesting work. As far as I understood, you have to design the stages beforehand so that people can label it. And I'm wondering how you would deal with tasks where maybe this is not so obvious to do. How would you do the stage labeling more flexibly or maybe infer it automatically?
Yeah, thank you for the question. I think a more easy way to label the stages is using the large language models, as the large language models has a very exciting comprehension ability. So we do use large language models and try to label the stages using Cloud Sonnet, and we found that the large language models can label these stages very good.
Right, thanks. But I guess you still, in the prompt, have to pre-design these stages and kind of provide this information to the large language model? Or how do you design the prompt?
In the prompt construction, we feed the model with a simple description of the text. Also, you can ask the large language models to divide the stage for you. For example, you can ask how many stages in this task.
Thank you.
Thank you for the talk. We totally agree that the different modalities have different importance at different times. I don't really see why this should be discrete or why you cannot have different weights like in sensor data fusion at different times. So why do you use these explicit phases?
So sorry, could you please repeat it?
Okay, we have different times where different modalities are important. Agreed.
Yeah.
But you have really phases, discrete times when this changes. I don't really see where this is important. I would assume that kind of weighing these over time, and so you have kind of 50-50 or 100, 0 or 10, and this is not that clear phases. In your case, yes, but usually I guess maybe not.
We don't actually use labels to tell the model which modality is more important. We let the model to learn the importance itself.
But as I understood, you have really phases. So there is phase A, and then there's a time, and then is phase B. Or did I misunderstand this? So in time, is this a discrete time, phase 1, phase 2? Or is this not the case in your model? Then sorry, then I misunderstood.
Sorry, maybe you can.
Okay, I come to the poster.
Yeah, thank you.
Okay, let's thank the speaker again.
Great job. Next up, we have Wei Kun presenting his work on TaiBot.
Okay, thank you for the introduction. I'm Wei Kun. Today I'm going to present our work TaiBot, learning to model Thai from visual demonstration through a real-to-sim-to-real approach. Class manipulation is a prevalent task in our daily life. It's worth studying how to enable the robot to learn such diverse and dexterous manipulation skills. So far, our community have already explored several class manipulation tasks. They are either easy to design reward for reinforcement learning. Some of them can accomplish with simple pick-and-place actions, and it might be easy to collect robot action data using teleoperation or kinetic demonstration. For example, the cloth folding task or unfolding task. But there's still a range of tasks that has not been explored. It might involve very complex object states, and it requires non-trivial actions to accomplish the task instead of simple pick-and-place. And due to the complexity of the task, it might be difficult to collect robot action data using teleoperation or kinetic demonstration. One of these tasks is tie knotting task I'm showing here. As you can see, it's a very complex manipulation task. Concretely, there are two challenges in this task. The first challenge is its complex topology. Here I'm showing the simplest type of knot, and you can see even in this simplest scenario, the topology is already very complicated. So if we want to design a learning framework to learn such manipulation skills, the learning framework needs to understand and represent the topology change in this knotting process. The second challenge is its complex trajectory. As you can see in this example, if we want to rotate and lift up this part of the tie, the hands need to move a specific trajectory instead of a straight line to accomplish this action. Therefore, the desired learning framework needs to learn elaborated object trajectory to know how to manipulate this object. As a result, we propose a real-to-sim to real learning from demonstration framework. Our pipeline takes in a human RGBD demonstration video as input. We first design a real-to-sim module to estimate the mesh sequence from this demonstration video and use this mesh sequence to guide the policy learning in simulation, and finally deploy the policy to a real dual-arm robot. It has several advantages. First, since we use mesh as representation, it captures accurate geometric structures and physics property of the type, which tackles the first challenge. Second, since we estimate a sequence of mesh from the demonstration video, it recovers elaborate trajectory of the type in a very detailed manner, and this tackles the second challenge. And as a bonus, it disentangles irrelevant information in the visual demonstration. Therefore, the human demonstration does not need to come from in-domain data. Now let's take a look into the detail. The first part is real-to-sim. Given a single RGBD human demonstration video and mesh at the initial state, our goal is to estimate the mesh sequence in following steps. Now we face the first problem. We have a mesh 0, and we want to estimate mesh 1. In this process, how to ensure its correct topology of mesh 1? Because topology is crucial in this task. And our solution is to integrate physics simulation in this process, and it can provide some physics constraints. Concretely, we load the mesh 0 into a simulator, and then manipulate the mesh in the simulator to get estimation results, and we do this iteratively. The following question is how to track objects' motion. We have image n and image n plus 1. We can first find local feature matching between these two consecutive images, which indicates the motion of the object. But we find that this information is not able to tackle the occlusion problem. Therefore, we amend this information with global-oriented key points detection. We define 5 key points with orientation on tie, and we predict its position and orientation on the point cloud. By combining these two information together, we get hierarchical feature matching. Given the previous estimation result mesh n, we can first find control vertices on this mesh by finding the nearest vertices to the feature points on image n. And 5 key points on the mesh will also serve as control vertices. The corresponding feature points and key points at next step will serve as the target position. We load them into the simulator and then manipulate the tie to the target position to get estimation results. Then we get a sequence of mesh. Our next step is to learn the policy, where we need to learn where to grasp the tie and where to pull the tie. At time step n, we have a starting mesh and target mesh. We first need to choose grasping vertices on this starting mesh. After choosing grasping vertices, we need to determine where to pull the tie. Since we already know the target mesh, we can retrieve the position of the grasping vertices on this mesh and use that as the target position. We then manipulate the tie in the simulation according to the trajectory of the grasping vertices, and this gives us a result mesh. By comparing the result mesh and target mesh, we can compute a reward for this grasping point selection strategy. We train this strategy in the simulation using PPO, and this gives us a teacher policy. But this policy cannot directly apply to a real robot because it uses privileged information. Therefore, we collect multiple robots from this teacher policy, rendering the point cloud in simulation and annotate it with pick and place positions. And then we train a student policy using imitation learning. We first evaluate our policy in a simulation. The left-hand side is the human demonstration we use, and the right-hand side is the policy rollout in the simulation. Our policy achieves 60% success rate in this simulation. And then we deploy our policy in a real robot model. And finally, we conduct qualitative evaluation on the real-to-sim module. The left-hand side is a real observation from the demonstration video, and the right-hand side is the estimated mesh from our real-to-sim module. We conduct qualitative evaluation on two types of knot. The first type of knot is the knot we use for real robot execution you just see before. And we also test another type of knot, which is shown in the last two rows in the slides. And the result shows that our real-to-sim model is able to estimate the mesh with correct topology, even in a very challenging scenario. Nonetheless, our pipeline has several limitations. First, it requires human effort to tune the robot actions in the last few steps. As you can see in this video, the way the robot knot the tie is slightly different from the human demonstration. That's because of the hardware limitation. And the second limitation is our real-to-sim model requires to know the mesh of the object at the initial stage, which prevents our pipeline to be fully automatic. Thank you, and welcome to our poster session for further discussion.
Thank you. We have time for 2 questions.
Hi, thank you for the presentation. Have you tried it with different tie knots that are like increasing in complexity?
Yeah, we tried 2 different tie knots, as you can see in the slides, but we only conduct physics experiment on one type of knot.
Did you try any that didn't work?
Sorry?
Did you try any tie knots that didn't work?
Yeah, sometimes it does not work because I found some randomness in the property of the tie. Like sometimes you perform the exact same action, and then the result is different actually. So that could be another challenge in this task: how to deal with the randomness of the tie's property and dynamics.
Thank you.
So how many human demonstrations were used for this one?
In this case, we use one demonstration, and it's kind of copying the motion. It's kind of copy the motion of the tie from the demonstration video. And I think definitely if you use more demonstration, and maybe you can achieve some generalization. Like you may learn some you may learn some kind of the shape. The shape might be different, and the topology is the same. And maybe you can learn some equivariance from multiple demonstration. And I think that will improve generalization.
All right, let's thank our speaker.
Okay, our next talk, we're gonna hear about physically embodied Gaussian splatting. That's presented by Jade. Welcome.
Hello, everyone. My name is Jad, and I will be presenting our work on physically embodied Gaussian splatting. Robots require an understanding of their surroundings to interact with and manipulate objects in their environment. Often in robotics, we compute an intermediate representation that captures some aspect of the physical world that is useful for downstream tasks. In robot learning, this representation tends to be a learned latent vector. And latent representations are attractive because they're simple to implement, but they require lots of data to generalize, they are not interpretable, and they provide no guarantees of physical correctness. Our work focuses on creating a structured representation with what we think are desirable and useful properties for robotics. Our representation, which we call embodied Gaussians, preserves the 3D nature of the world, is physically constrained, can be forward simulated for prediction purposes, and can be corrected from new observations in real time. Recently, computer vision methods like 3D Gaussians and neural radiance fields have shown a remarkable ability to capture the visual and geometric aspects of the world from only posed images. Gaussian splatting does this by modeling the world as 3D blotches of color encoded as Gaussians. Given a set of cameras, the Gaussians' positions, rotations, scale, color, and opacities are optimized so that they render into images that are equivalent to what is being observed. With a sufficient number of cameras, the optimization procedure recovers the true geometry of the world. And this is a really powerful result because it means we can construct a 3D representation from only images in a model-free way. The problem is that the original Gaussian implementation cannot be used to represent the physical state of the world. Because it is designed for static scenes and not dynamic scenes, it has no means of updating itself in a physically consistent way when the changes in the world occurs, and we are unable to predict future states of the Gaussians from their current state. What we propose then is a dual Gaussian particle representation, where the particles and the Gaussians work together to represent physical state. The Gaussians encode the visual aspect of the environment because they can be splatted, whereas the particles represent the physical aspect of the world. They are acted upon by a particle-based physics simulator, which enforces things like objectness, correct collision behavior, and kinematic relationships. The Gaussians are connected to the particles through something we call the Gaussian particle bonds, which are rigid transforms. As the particles move or are moved by the simulator, the Gaussians are transported along to maintain these bonds. Our system works in two phases. The first phase is the initialization phase. In the second phase, we keep the Gaussians and the particles that we find in the initialization phase synchronized with the real world through a combination of forward prediction and visual correction. And this runs in real time at 30 Hertz. So to initialize the Gaussians, we use 5 viewpoints, with each viewpoint producing an image, a depth map, and an instance mask. And we note that the depth and the instance is only needed for the initialization phase. To begin, we compute 3D bounding boxes which are loose around each object. We then fill each bounding box with a grid of spherical Gaussians. Any Gaussian that does not project back into the instance mask is removed. And then we optimize the Gaussians to minimize the reconstruction loss on the images and the instance masks, except in this optimization procedure, the Gaussian scales are not allowed to change, so they stay spherical. And also, they are not allowed to collide with each other or with the ground. We do this for a predetermined number of steps, and then wherever the Gaussians end up, we spawn particles at those locations. And the particles that belong to every object are then connected with shape matching constraints, which the physics understands. And finally, we allow the Gaussians to continue training, except this time the scale is allowed to be optimized, and the densification procedure that comes with Gaussian splatting is also enabled, so the number of Gaussians can change. So here are some examples of what this initialization procedure outputs. So once the scene is initialized, the system begins running a prediction and correction loop at 30 frames per second. We only use 3 cameras in this phase and only require the RGB images. At every time step, we begin by reading the latest images and joint positions from the robot. Then we run a single physics step that calculates the position of the particles on the so it predicts the state of the particles given the constraints and the dynamics at that time. And then we optimize the Gaussians to minimize the visual discrepancy that has occurred as a result of these physics steps. The displacements the Gaussians undergo during this procedure are converted to something we call corrective visual forces, which are imparted upon the particles that the Gaussians are connected to. Finally, we reset the Gaussians back to where they were originally, and the visual forces are then resolved at the next physics time step. And the effect of this is that the scene is updated in a physically constrained way to minimize visual discrepancy. We evaluate our method's ability to continuously track the state of the environment on a tabletop setting. We use 3 cameras to observe the scene and 2 cameras for evaluation purposes. We show our system tracking the state of the physical world in a scene where a robot is pushing around multiple objects for a relatively prolonged period of time, which is around 1 minute. We also show that our method is capable of modeling a deformable object and is also able to continuously track that state. We show it on a pick scene. And lastly, we show on a scene where gravity prior plays a significant role in aiding tracking. So currently, our system has several limitations. The first limitation is that this is designed to work in a controlled setting where strong assumptions can be made about the number of objects that are in the scene. If we want to extend this to the open world setting, then we need a way of initializing objects as they enter the scene. Second, our initialization method does not model cavities and requires objects to be visible from most viewpoints. If we want to extend this to cluttered scenes, then we'd likely need a different initialization scheme, which hopefully would might be like learned from a data set of common shapes and can do shape completion. Lastly, we distill the corrections into visual forces, and this makes our system very simple to implement because the physics engine does not need to know about the rendering pipeline. But because of the second-order nature of the forces, we get some oscillations in the objects. So some tuning has to occur to minimize the oscillations, but also increase the tracking accuracy. So I'd like to conclude by mentioning some future directions we have planned for this work. We have shown how to encode the visual and physical aspects of the world, but we can easily add a semantic dimension to this by baking in descriptors from foundation models like Dino or Clip at modeling time. And this would allow our representation to be queryable from a semantic perspective, which adds some utility to this. In addition, from the control perspective, we look to leverage the rich state that this representation is encoding, as well as this real-time nature, to service algorithms like RL, imitation learning, and other things. So thank you very much for the talk. That concludes it. Thanks.
Any questions from the audience?
Hi. Thanks for your talk. Currently, I see your method is only applied to reconstruct the scene and do novel view synthesis. So is there any possibility to apply the method to simulate the physical future states of the world? And will there ever be some new challenges of your method to do that? Thanks.
So you don't need to run the visual correction step. You can just run it as a physics simulator, in which point you're basically predicting the future states. And then at any point that you receive the observations, you can then continue tracking it.
Thank you.
My question was also about the physics simulation. So where did you get the different constraints from? Like you had the rope, for instance, that was like soft but connected.
Yeah.
And obviously, when the robot collides with something, it seems like you make the assumption that the robot will always win and the object will yield. But objects also collide with each other and all of that stuff. Where do the constraints come from?
So the idea behind this work is a lot of the times we know what the physical priors are, so we don't have to learn them. So, things like collision, things like gravity, things like where the robot is and its kinematic relationships, how do we leverage that in this representation? So to answer your question, we manually, because it's a controlled environment, so we assume that we know what the constraints are, but they don't have to be so accurate. They just need to be good enough so that the visual forces can correct them at the next state.
Right. Okay, so you could also put in a constraint where the cup would be soft and bent like a rope.
Sorry, what was the last part?
Like you could have put in an assumption that the cup would be as soft as the rope.
Yeah, you can make it a deformable body if you wanted to, not necessarily rigid.
Okay.
Great, let's thank the speaker again.
All right, next up we have Priya to present RT Sketch.
Hi everyone, I'm Priya, and today I'm presenting our work RT Sketch, a goal-conditioned imitation learning agent which operates from hand-drawn sketches. So imagine you're asking your household robot to help you set the table for Thanksgiving. You might start with a language instruction like, put the utensils next to the plate. And a competent robot might come up with a plan that looks like this, where the fork and the knife are next to the plate, but are on either side of each other. Maybe what you actually had in mind is for the fork to be next to the knife, on top of the napkin, on the right side of the plate. We can quickly see how language can either be underspecified or can become very lengthy in order to accurately specify our spatial goals. So instead of this, you might decide that it's just easier to show the robot what you mean. And you go on Pinterest and you find a table arrangement that you really like, such as this one. The challenge here is that a goal image such as this encodes a lot of unnecessary information. So for example, the decoration on the table is completely different, the tablecloth is different, and so the robot might struggle to understand which visual features to attend to. What we see in the setting of goal-conditioned imitation learning is that while goal images can be very useful for conveying our spatial intentions, they're often not always available and are often overspecified or environment-specific. And on the other hand, language is super easy for us to give on the fly, but can often be ambiguous or needs to become very lengthy in order to more accurately describe our goals. Ideally, we'd have some goal representation that's both spatially unambiguous and easy to provide on the fly. In this work, we argue that hand-drawn sketches can serve as this happy medium for goal specification. We present a policy called RT Sketch, which learns to take as input a hand-drawn sketch of the scene and to output robot actions that achieve alignment with this goal. So for in this case, putting the Coke can near the Sprite can. We train our policy to take a goal sketch and a history of image observations as input and output actions. At the input, we specifically assume access to RGB images of the robot's current state and a goal sketch. These can be concatenated and fed through a transformer architecture which outputs robot actions to be executed. The main challenge in our work is how do we actually get these sketches? It's very time-consuming and painstaking to have to draw a sketch for every single robot trajectory you might collect. So to get around this, we train an image-to-sketch conversion GAN, which learns to take ground truth goal images and map them to sketches, given a very small amount of paired data. To train this GAN, we take ground truth goal images, for which we have manually drawn sketches consisting of 500 paired examples, and the network learns to predict sketches given these images. We can then apply various post-processing techniques like changing the thickness, the color, or even the affine warping of the sketch to produce more diverse sketches for the same image inputs. And using this pre-trained network, we can then take any large-scale robot data set and take the terminal image of each episode and convert it to a synthetically generated sketch with which to condition our policy. In this way, we're able to train RT Sketch on a large-scale data set of 80,000 trajectories while only having access to 500 manually drawn sketches, which is less than 1% of that entire data set. We aim to evaluate how well RT Sketch compares to traditional goal-conditioned imitation learning agents like a language condition baseline, RT1, and a goal image condition baseline, RT goal image. We're interested in how well each of these methods can achieve alignment with a given goal, but this is actually very non-trivial to define. So we come up with two metrics to assess goal alignment. In the first, we present human annotators with a ground truth semantic goal, a ground truth visual goal like an image or a sketch, along with a policy rollout video, and we ask a human evaluator to rate on a scale of 1 to 7 how well the given language instruction or given rollout aligns with the semantic or spatial goal. We also want to quantify how well each policy is able to achieve spatial precision. So we report the average pixel-wise error in achieved versus ground truth object states. Let's first take a look at how RT1 performs. When we evaluate RT1 on the kinds of benchmark manipulation skills it was trained on, we can see that the policy performs very reasonably as expected. A goal image policy similarly makes progress towards the task, but it has this unexpected behavior of over-attending to these pixel-level differences, causing the robot to repeatedly retry and actually leading to more failures than successes. RT Sketch, on the other hand, is able to complete these manipulation tasks along with a range of other tasks we evaluated, and sketches help the policy avoid over-attending to these pixel-level differences. So in terms of the perceived spatial and semantic alignment, we see that RT Sketch is on par with these traditional baselines, indicating that sketches are a valid and expressive goal modality. We also find that in terms of the precision of each policy, RT Sketch achieves far lower spatial errors than RT1, and this is because sketches can encode a lot more spatial information than can be expressed in language alone. Now that we've validated that sketches are an expressive goal representation, let's take a look at how our policy performs on a range of input sketches. Here we can see that RT Sketch is able to handle sketches that range all the way from roughly drawn minimal sketches to more detailed colored representations. And this also holds for sketches drawn by annotators whose data was never seen during training. Because our policy is able to deal with very minimal sketches, this is especially useful in the case where you might have visual distractors in the scene or a table with a lot of clutter. In these situations, a goal image policy tends to get very confused because once you add clutter to the scene, there's a huge visual domain gap between the observation and goal image, and a goal image policy might get confused and just start manipulating objects at random. But RT Sketch, having been trained on minimal sketches which abstract away much of the pixel level details, is still able to complete these kinds of tasks. So we see a marked performance improvement with RT Sketch over RT Goal Image in this case. And similarly, in the case of when language is ambiguous, sketches can especially be favorable. Here's an example where we task RT1 with this very abstract goal of completing the rainbow, which requires the robot to reason that the existing objects on the table are arranged by color, and the blue chip bag needs to be placed next to the green Sprite can. Because this is very out of distribution for RT1, the policy becomes completely confused and just starts opening a drawer, while RT Sketch is able to complete this kind of task given a very rough initial sketch of the scene. And while we've shown so far that sketches can be a useful goal modality compared to existing ones, we're also in the future really excited by the prospect of combining sketches with existing modalities. So in cases where, for example, a language condition policy or a sketch condition policy can suffer on their own, when we train a policy conditioned on both, we're able to see the benefits of using both, for, in this case, encouraging the can to be reoriented, but also placed in a desired spatial location. And while our policy is not without failures, we're really excited by the prospect of moving towards more abstract goal specification in the future. And we encourage you to check out our website with our most recent results deploying RT Sketch on new robots like the Franca, new IL backbones like diffusion policy, and simple sketches like just arrows. Thank you, and I'm happy to take any questions.
Great.
Hello, thank you for the really interesting talk. This project reminds me of Platonic form. So I was wondering, have you guys tried the perfect geometrical shape instead of sketches? This is my first question. And my second question is on the cluster table example, why did the robot choose the purple chips instead of the green chips to do the task?
Yeah, thank you for the question. So if I understand the first question correctly, it's on like if in the future we can condition the policy on more geometric diagrams or things like that.
Yes.
And so we haven't directly tried that yet, but I think that would be really interesting. And actually, like the motivation for this work was looking at IKEA manuals and how we can eventually move towards those more abstract representations. So I think that's something we're really curious about in the future. And you're definitely correct to notice that in the distractors setting, it moved one of the chip bags, but it could have moved the other. And I think in those cases, when even the sketch is ambiguous, the policy will basically reflect the biases of the data it was trained on. So in that case, you know, like moving to the left happens to be more represented in the data, so that's what the policy does.
Okay, thank you.
Mm-hmm. Okay.
Hi, thanks for the nice presentation. My question is, so the sketches you provide are from the same angle as the camera, right? Have you tried, like, what is the maximal discrepancy between the sketch and the actual camera angle?
Yeah, that's a great question. So when we collect the sketches to train on, we do trace them over the image, so it's camera aligned. But then we apply a lot of like affine warping so that it's trained on examples where it's not perfectly aligned. So we see that like with completely, when the perspective is totally off, there is a small performance drop. But I think like even from the traced representations compared to like edge detected images, there's almost no performance drop. So that's about like the lower end of what we can handle currently. Thank you.
Okay, thanks.
Let's thank our speaker again.
Okay, now we arrive to our last oral talk for this session. So it will be given by Joey for Remix.
Thanks. Hi, everyone. I'm Joey, and I'm here to present our work on automatically weighing data mixtures for large-scale imitation learning. So there's been a lot of interest recently in training big generalist policies like Octo or OpenVLA. And the hope of training these large policies is that they're going to be able to generalize well to lots of diverse tasks and scenarios because they've been trained on lots and lots of data. And so, the general formula looks like this. We start with some policy, normally a transformer, and we decide that we're going to train it with a behavior cloning loss, which just minimizes the negative log likelihood of the data. And the question is, what data do we actually train this on? Well, recently there was this huge effort called the OpenX embodiment collaboration, which basically pooled a bunch of data sets from academia and industry to create one of the biggest collections of robot data sets out there. And most of these models, like Octo and OpenVLA, have been trained on this data set. So we simply take all the OXE data, convert it to states and actions, and train our model, right? Well, unfortunately, if you do this in practice, and this is one of our experiments from an early run of Octo, you can see that the policy is not very precise, and they don't end up working very well. And so what actually happens in practice with these models is we'll take the OXE data set, and then our collaborator CoRL will come in, and he'll come up with something that he calls his magic soup. So CoRL will look at all of the data, and he'll say, you know what, there are 90 data sets in OXE, but I'm not going to train on all of them. I'm going to take 42% of bridge, 8% of cable routing, 19% of the UR5 data set, and 31% of the RT1 data set. And that's actually what I'm going to use to train my policy. And so the question that we ask in this work is, how should we automatically curate these data mixtures that seem to actually work for training these large generalist policies? And so what we really want is a policy that works on lots of diverse tasks and scenarios, but we can't really measure that at train time. So instead, what we say in this work is, instead of looking at test time tasks, because that would be really hard and kind of cheating, we're going to see if we can train a model that will get good performance across all of the different things that it's seen at train time. So we'll split our data set into these different groupings or domains. In this case, it's sort of the different data sets within OXE. And we'll say, how can we get good performance across all of them? And how can we design a data mixture that does that? And so the answer that we come up with in this work is we're going to try and minimize the worst case loss across all of the groups that we see at train time. And so this kind of looks like this. We're going to take each one of our domains, and we'll estimate some loss quantity that measures how well we're doing on that domain. And then we'll weigh the domain by a certain coefficient, in this case alpha I, and sum across all of them. And the minimization of the worst case scenario comes in where we maximize sort of over this weighing of all of the different domains to sort of maximize this overall loss quantity, and then we'll minimize the parameters after that. And this should look a lot like robust optimization, well, because it is kind of a robust optimization. And so the question that we have here is sort of, what loss measure should we really use for this? And what we do is we're going to first start by training a reference model. So we're not going to directly take the behavior cloning loss. We're going to use a reference model to estimate how well we can do on each of the different domains first. And then using the reference model, we'll measure what we call the learning potential of each domain. So this is basically the gap between how well the policy is doing and how well the policy could do if it was trained to convergence on a given domain. And so this sort of estimates how much we have to go in terms of fitting this domain. And so using that, we introduce our method, which is called remix, or reweighing robot domain mixtures. And we're just going to do a robust optimization over sort of this learning potential. And so as you can see, this is the same equation from before, which is the robust optimization, and the blue terms are that learning potential that we're trying to optimize. And so when you run this optimization procedure, what's going to happen is basically we will start upweighing the domains that have a high learning potential so that we haven't fit very well, and we'll end up downweighing the domains that don't have very big learning potential. And then at the end of training, we'll take all of these alpha coefficients, we'll average them, and we'll use those as data set weights that we can use to determine a data mixture for training downstream generalist policies. And so now you might be asking, okay, I've described this optimization procedure. Does it actually work in practice? And I'm going to construct a simple example to show you that it's a little bit more complicated. So let's say that I design one domain, which is just the bridge data set. And so as you can see, it's a simple pick-place manipulation data set, but it's very, very big and very nice. And so we have a second domain, which is going to just be some Gaussian random noise. The key distinction here is that the Gaussian random noise is going to have larger variance in the action distribution than the bridge data set. So hopefully this makes sense. And so I'm going to run my robust optimization procedure on these two domains. And what's going to end up happening is I'm actually going to prefer the Gaussian random noise to my real robot data, which doesn't really make sense initially. But if you look at it, the reason for this is that the Gaussian random noise has a larger loss magnitude. And so implicitly, it's just going to kind of be preferred by this thing, which is trying to maximize the loss quantities. And so to fix this, we introduce a few different adjustments, which we call our remix recipe. So the first is action normalization. So we'll take all of our different embodiments, which have different action magnitudes, and we'll normalize them to a common Gaussian distribution. And this helps balance the loss magnitudes across different domains and sort of eliminates the previous problem. A second problem that we encounter is multimodality. So here's an example of an environment where an agent has two options. It can sort of push the object to the left or to the right, so there's two different modes. And if you use sort of an MSC style loss on this to fit continuous actions, you can often end up with something that doesn't look like it's actually fitting the data very well. And so you have this problem where continuous losses sometimes will be unsure of which mode to fit, and so they'll do really poorly, even though the data for this environment is very clean. So to fix this, we discretize our actions, and we use a discrete BC loss, and that helps us address the multimodality problem. The final problem that we often encounter in robotics, especially, is overfitting. And so we employ aggressive early stopping when we do this domain mixture procedure. So for example, let's say I have one domain, which is the bridge data set. It's very large, and so we can achieve low validation loss on it. But we have another domain, which is the Berkeley UR5 data set, and it's not as big, and so our validation loss begins to increase, and we start quickly overfitting at that domain. However, at this point, we don't have a very good measure of our validation loss, and so we can't really appropriately do the robust optimization. So to fix this, we do aggressive early stopping on the reference model, and that helps us control the overfitting and get accurate estimates. So if you put all of these together, we can look at the resulting weights after all of the adjustments we made, and we can see that it tends to come up with things that make sense. So if I take the Berkeley UR5 data set and I look at it, the excess loss, or this potential improvement, is large. So that means our reference model has much lower loss than our current model, and so we see large potential improvement. And that means we're going to upweight it in comparison to CoRL. So we end up doubling the weight of this data set in the overall mixture. Conversely, you can look at the ARM Farm KUKA or QTOP data set. And this data set we find has a much lower potential improvement. And that's because it was generated by a learned policy and is maybe visually harder to discern the actions. So we actually don't do as well on this data set, and there's small potential improvement. And so we end up weighing it at only about 50% of what CoRL weighted in his original data set mixture. Okay, so I've shown you that intuitively the data set weights that are determined by this procedure can make sense. What does it look like experimentally? Well, I'll take all of the data sets used to train the RTX models, and I'll learn a data mixture on them and weigh that at 95%. And then I'll collect some small amount of co-training data. And then I can train a goal condition policy using all of this data and evaluate it on some generalization tasks. And so compared to CoRL, we see that we do better at new objects, new object initial positions, and even on embodiments like the Franca, where in this data mix there isn't that much actual data. And so although CoRL's weights improve upon human performance, or sorry, uniform data set weighing, the remix weights do better, improving performance by 32%. So I'd encourage you all to try it out. And if you have more questions, feel free to talk to me at the poster. Thanks.
Great. Any questions from the audience? Yeah, there are some hands up. There's one in the back. I don't know whether.
Hi, Joey. Here. Thanks for the interesting talk. I'm wondering, so you've described one way to get better signals out of the learning potential, which is to mitigate the problem of checkpoint selection, right? Early stopping everything. But in practice, if you have a large enough data set, collection of data sets, then co-training on all of them, there's also problems about capacity if you train this reference model. So how do you kind of think about normalizing the capacity of the model?
Yeah, so that's actually one of the current limitations of this approach, is that if I have some very, very small data sets that I overfit quickly, it's really hard to estimate the learning potential, as you mentioned. And so, yeah, that's still like something that we're working on figuring out how to address. But if you have a really small domain, it can be difficult. One thing you can maybe do is pool together multiple small data sets into one bigger domain, and you can measure just like, okay, on these tail cases, how well am I doing, and sort of weigh them as a group. And that might help address that problem. But yeah, low resolution, very high resolution, fine-grained things with very small domains gets very tricky to make these measurements on.
Makes sense. Thanks.
Any other questions?
Thanks, very interesting work. Do you think the answer to this optimization problem is a static answer, or is it more of a time series kind of thing that the mixture is going to change during the training steps? Because some of the papers have that they change their soup during during the training. What do you think about that?
Yeah, that's a great question. I think in this work in particular, we found that the algorithmic decisions that led to good data set weights were not the same as the algorithmic decisions that led to the best policy. So for example, in the end, we trained diffusion policies, but the diffusion loss isn't great at sort of estimating the learning potential because it's sort of using a lower bound. And so we found that in practice, sort of doing the data set weights separate from the learning procedure was better, and that's also because sort of robust optimization in practice doesn't lead to as performant models as just sort of things that are trained just on the normal objective. That being said, I think there's room to improve by sort of thinking about how you could do on-the-fly mixing, and so I think it could be an interesting thing to look at in the future.
Great, let's thank the speaker again, and then we'll move on to the exciting keynotes.
Good afternoon, everyone, and welcome to our third keynote of CoRL. It's my absolute pleasure and honor to introduce Professor Jitendra Malik from UC Berkeley. Jitendra is a towering figure in computer vision, graphics, machine learning, and robotics. His work has won 11 Best Paper Awards, 6 Test of Time Awards. His H-index is 171. And when I checked today morning, he has more than 230,000 citations. Some of his most influential works, have made it into your, phones that you're holding, the, high dynamic range work. Then one of his very early works was anisotropic diffusion. That name might be familiar to some of you. Then he laid the foundations for the beginning of image segmentation with the Berkeley segmentation dataset, which then laid the foundations for works like RCNN to come along. And more recently, he has gotten very involved in robotics with some very exciting work in how we can leverage simulation to build very exciting and performant robotic systems. So Jitendra is not only a researcher, and research is not just about doing research, but also about paving the future. And sometimes that means that you have to take controversial stances, which might seem controversial at the time they are said, but only to be realized in the future how true they were. So, Jitendra is known for his hot and spicy takes, and I hope we'll see some of them in his talk today. And I'm very much looking forward to it. And Jitendra has always believed in interdisciplinary research, right? And sometimes when we look at the problems of action and perception, they might look very different when thought of them individually than how they look when you think of them together, right? So with that, Jitendra, it's an honor to have you. And we are very much looking forward to your talk and your spicy takes.
Okay.
And if you want to continue, you can find Jitendra in a bar playing backgammon or dumb charades.
Yeah, thank you. Thank you, Pulkit, for this very generous introduction, and thank you to the CoRL committee for inviting me. It's a great pleasure to be here. And I'm going to talk about robot learning with inspiration from child development. So I always like to start with my credo. So this is sort of a statement of religious belief. So for me, my religious belief is that we cannot explain or understand artificial intelligence without knowing about the natural variety of it. And the natural variety of it, it only makes sense in the context of evolution, like all biological capabilities. So something like, many million years ago, like 540 million years ago is the time of the Cambrian explosion. And that's when you have the first multicellular animals. And they got a benefit out of moving. Why? Because then they could go to food in different places. But then you need to know where to go, which means you need perception. So the beginnings of intelligence are in this loop of perception and locomotion in this case. So action, but it's locomotion. And there is this great line from the psychologist Gibson, we see in order to move and we move in order to see. And we in computer vision over its long history have sometimes forgotten that the primary purpose of vision is to guide action. Now, speeding up a bit ahead, we have the first time when the humans split off from the primate line, and then you have the emergence of bipedalism. So we walk on 2 feet, so then our hands are free, and then the hand develops, and there is this quote from the Greek philosopher Anaxagoras: it is because of his being armed with hands that man is the most intelligent animal. And in fact, the fossil record supports this. So the development of the hand and tool making leads to the development of the brain. Okay, and then at some point, like maybe 100,000 years ago, maybe 1 million years ago, you have language and all of what that signifies. But the big point that I want to make is, if we think of the development of intelligence as spanning 24 hours, then language is in the last 3 minutes or 5 minutes, which is fine, it's great. We all need language, otherwise how would I be communicating with you? But in the big scheme of things of intelligence, we should keep that perspective. So what are the central problems of intelligence, if you will, but from this perspective, right? So you got locomotion, you got navigation, which is going to where you are, and then the emergence of humans is tool building and navigation. So therefore, it's obvious. When you look at it this way, what are the central problems of robotics? They have to be locomotion, navigation, and manipulation. And this should not be any surprise. I mean, if you open up any robotics journal or proceedings, these are the topics. But they come very naturally. This is all about, my definition here is connecting perception to action in the physical world. So let's start with a bit of a whirlwind tour of where we are in these 3 domains of robotics, okay? So I'm going to do this with a biased sample, obviously work that I was involved in or my group was involved in. So let's start with locomotion. So this is a paper which is going to be presented at NeurIPS, and we have previously worked on quadruped locomotion, but these are results on humanoid locomotion. And for those of you who have been in the Bay Area, you should recognize all of these as various sites around San Francisco. I will come later to how this was trained, but the point here is to show how robustly this robot can walk. And then it can walk in rugged terrain. So these are hiking trails near Berkeley in the Tilden Park, and we can do that. And okay, so that's success in locomotion. Navigation. So in navigation, I'll talk about this line of work called GOAT, Go to Anything. This was presented at RSS, and this is with a lot of colleagues from Meta. And the setting of the problem, I want to tell you about the setting of the problem, which I think is important, because I think for robotics, doing good experimentation and good testing and good benchmarking is more challenging than it is for vision, but it needs to be done. So the setup that we did was, we rented random Airbnbs, and then you put the robot inside, and then the robot is given the task. Go to some location. So in this case, the location is shown as some goal. So here, if you look at that goal, which is at the top in the middle, that's like a kitchen sink. So the goal can be specified by a photo or by some phrase or in language and so on. And then the robot sees something. So what it is seeing currently is shown by this observation. And then it has to find that target. And as it finds the target, what it is doing is it's building up a spatial memory, some kind of a map. And then it keeps moving around. And it's building the map, and it is recording the objects that it sees. Okay? And then you can see that list of objects that it sees. As soon as it has success, right, it's found the kitchen sink, then it's given a next goal. So this is this teddy bear. So it's going to move around until it finds a teddy bear. Then it's trying to find a red cup, et cetera, et cetera. And so on, it proceeds. And I insisted on this test, that you go into a random Airbnb and just put the robot down and it has to find location. Now this to me is the kind of test that you need to have for various manipulation capabilities. If you think your robot can do a capability X like open drawers, okay, just rent a random Airbnb, put down your robot, and then let's see what it does. And this is the way to avoid fooling yourself, okay? So, and then we find that the performance actually is very good. It's on the order of 90%. And the failure cases are actually due to perception. It's really, in my hat as a vision person, we haven't done our job well enough. And as vision gets better, this will get to. So the parts which have to do with exploration, map building, and so on are essentially perfect now. Okay. And we evaluated it on like 200 different object instances. And by the way, we have earlier papers which compare this to end-to-end policies. And end-to-end policies do not work very well in the wild. They tend to overfit. Okay, so, okay, manipulation. So here, I'll show you what we have. This is a recent, or not so recent result from this is a bimanual manipulation task. So personally, I believe that the future of manipulation is a dexterous manipulation, which means 2 multi-fingered hands ideally equipped with tactile sensing. And this is the kind of stuff we can do. So here, this is the popular paradigm of the day. You collect teleop demonstrations, you train a diffusion policy, and so on. But what we are doing is we are doing this with multi-fingered hands in a bimanual setup, and yeah. And some of these, it would be difficult to do with 2 parallel jaw grippers. Okay, so this is where we are. And then the question is, are we done? How close to solved are we? So if this was a general audience, I would actually make this a quiz, but we are all sophisticated robotics researchers here, so we know the answer, right? Navigation is nearly done. Locomotion is not fully done. It's probably done for quadrupeds, not for humanoids. And I mean, but we know the machinery. In a couple of years, we can keep turning the crank. And in my group, we stopped working on quadrupeds because we thought we were done. Okay, and because the basic machinery is there. Manipulation is the hard one. Manipulation, there's a long way to go. And then, of course, in this era of deep learning, the question is why, and Moravec's paradox is very truly applicable. And one way to explain this is in terms of data. So the way language and vision got made very big progress, it's much harder for robotics because we don't have that kind of data. So that means you can view that as a challenge, but actually it's an opportunity. It's an opportunity because this makes us think, and we think about efficiency in data use. Okay, and if you look at the literature on child development for language development, it's the case that a child has, by the age of 10, has maybe heard 100 million words, whereas we are talking of like 1 trillion words for training an LLM. So there's an inefficiency factor in terms of data size of 10,000. So if we were smarter about how to make use of data, then as smart as human babies are, then we would need 10,000 times less data. And it might be wise for us to make use of that insight in robotics. So what I'm saying here is not a novel insight to me. It was actually first stated by Alan Turing. So Turing, in that famous 1950 paper, if you take the trouble to read all the way to section 6, he has this line. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? And then you go through the sequence of child development. And this was 1950. In the last 75 years, we have learned a lot about how children develop. Our colleagues in psychology have done an amazing job with a series of experiments and theories and so on. And this can guide us. And I've spent a lot of time in that literature, and it's actually fun and worth reading. And here is a paper which I keep referring to in all my talks because it's one simple summary of the literature. If you don't want to read 1,000 papers, just read this one. At some point, you should read the 1,000 papers, or at least 100. So these are kind of principles based on studies, observational, experimental, done with kids, right? But let me convert those into some design insights for robotics, or actually AI in general, because I think robotics is central to AI, okay? So for example, multimodal means vision, touch, and proprioception. All of these should be used. Incremental means that don't think of everything being end-to-end. I think this is a silly idea. There are hierarchies of control and planning. Be physical, which means that embodiment matters, okay? Explore, I'm just converting it to sort of computer science lingo, so search is okay. Be social, we learn from others, well, that's imitation learning. And then use language, so here what I'm saying, what everybody's saying, right? Okay, LLMs might help. Fine. I want to now jump into specifics, but I want to take you through a little bit of my intellectual journey, in the sense that I've spent like 40 years of my research career in computer vision, and I got into robotics like 7 years ago. I got in through navigation, which I think of as a gateway drug for vision people, because navigation is mostly a vision problem, basically. I mean, the robotics part is fairly small. I think it's really a vision problem. And when it fails because vision has failed. Anyway, the key insights that I felt were important, or at least it was realization to me, was that in vision, we focus on the generalization problem. We are using this pattern recognition as a paradigm. And the key thing is generalization. So you have to recognize a cat, and there can be many breeds of cats in many poses, in many lightings, in occlusion, blah, blah, blah. Okay, but when you have motor control problems, I mean, whether in biology or in robots, there is an additional aspect, which is sort of the control theory aspect. And control theory brings a couple of things. One is this ability to deal with small disturbances, right? And that's what feedback control is all about. But there is this other aspect, which I think is also important when we talk about control in the context of robotics, which is adaptation to varying physical conditions. And this, in fact, has also been studied by control theory people. There's an area called adaptive control, which goes back to the 1960s. They would study problems like there's an airplane which is flying, and then you have a certain amount of fuel, and over the course of the flight, most of the fuel has been used up, so the mass of the airplane is different. So maybe your control laws should be slightly different, things like that. But of course, the tools then were much more about linear dynamics and so on, and we have fancier techniques today. But that's what we should do. Am I okay? Can people hear me in the back? It's great. Okay. So anyway, so to me, this is going to be central about what I expect for success in robotics: generalization. So don't show me that you can pick up one specific object. It has to generalize across a variety of objects. Or if you're walking, it has to generalize across a variety of terrains. And then this sort of, there must be robustness, like in the control theory kind of sense, and then adaptation, which I think of as happening over time in a certain sense. So time has a role, because when you're doing physical activity, time has an arrow. Okay, so with this is like the philosophical context. I'll talk about some of the work from our lab in the last several years, and not going into details, but this is a paper, Rapid Motor Adaptation. And the insight here was really, we're going to train this robot in simulation and so forth, but what were we after? We were after this problem of adaptation. We wanted to have one policy. I mean, we have all looked at the amazing results that Boston Dynamics has, right? They have great controllers that they are able to design with a good model, and then you have different controllers for different situations. No, we wanted to use the power of neural networks, which is that they are nonlinear. I mean, duh. But so what we need is a way to work in many, many different settings with one policy. Okay, so what's the insight there? Somehow you need to have a way to smoothly switch between different policies. And that's this variable z. And this z is going to be, so we have this policy which is getting as input previous states, previous actions, and then it's producing a new action, which is, say, joint angles. So you need to know some aspect of the environment which is going to be captured in this variable z. And this has to be estimated online. And the trick is that this can be estimated from some past history of the robots moving in the environment. And let me just explain this with this demo. So here's this robot which is walking. And this mattress has got plastic, and there's some olive oil which has been spread on it. So the robot is going to have some trouble. So see, it starts to slip, and then it recovers. Now, what's happening during this recovery process is that this z, this latent 8-dimensional vector, is being estimated from the fact that it started to slip. So from how the robot's body responds to a certain sequence of actions, you can infer something about what's happening here. And then the result of this was that we were able to train this robot. We took it out in the real world, and zero shot, it performs very well. And basically, all these results are zero shot. All the training is in simulation. You put it out in the world. And then in all these different environments. So this is very satisfying, because this is that dream of adaptation, right? And in more recent work, we have used different machinery. So that was like simple neural networks, multi-layer perceptrons, and so on. Now, if you throw some heavy machinery like a transformer, right? Now, what you might hope is that if you have enough temporal history, you have in-context adaptation. And does that happen? Actually, it does happen. So here's an example. So here's this robot walking. So notice that it's taking shorter steps. And then when it walks on flat ground, it's back to normal. So here we didn't have to have this explicit this adaptation in the RMA style of estimating the z, but something like this is happening inside. And you can, in fact, if you do sort of neuroscience on your neural network, and you look at the neurons and you look at the weights, you can see that in the hidden state of certain neurons is capturing this transition in the environment. And you can also do some t-SNE plots of and see the same thing. So inside it, adaptation is occurring. It has to occur. But we have adaptive control. It's like the control theory people were talking about it in the 1960s with the tools of deep learning. Okay. By the way, all these robots were blind. So what do you need perception for? I mean, blind people can walk, but they walk more slowly and more hesitantly, and they will not be so comfortable crossing a river on these stepping stools. Okay, so this is a paper which, in fact, we presented 2 CoRLs ago. And I won't get into the details here, but it's the same RMA philosophy, that there you have this z, but in addition you have this gamma, which somehow captures the terrain. But very importantly, we did not do what is a standard thing in a lot of the work coming from the control tradition, which is footstep planning. I mean, footstep planning to me is a crazy idea for walking, right? You don't, when you're walking, if you are spending all your time planning your footsteps, you're not going to have time for anything else, right? No, that's not what we do. We might do footstep planning when we are children at age 1.5, but even there, I doubt it, right? You don't want to be doing it. There's an interesting question of why building a local map is also a bad idea. And it's because of the noise. As the camera, the robot moves, there's enough shake. So if you're trying to do SLAM-type techniques, you will have enough noise in your environment. So here, the end-to-end paradigm is actually good. And we were led to it, in fact, from studying some of the work on how children learn to walk by Karen Adolph at NYU. You really want to think of it as an end-to-end policy, because what you need for walking is not the full environment reconstructed. But you need to get your footholds, and it has to happen implicitly. Anyway, so this is the final policy. So our slogan is no gates, no maps. And this is the result. So this robot has no prior knowledge of the environment. It's what it sees. It has an RGBD camera. And then it's walking, and of course, if it's a very perilous walk, because if even the rear legs don't land in the right place, it's going to fall. And that does happen, but it's like 1 in 10 trials. And then climbing stairs and so on. I mean, this was all impressive 3 years ago, but it's not anymore. Okay. So I'll move on. Okay. Now let me talk a bit about. So that was locomotion, and I'm very bullish on locomotion. I think this is the place where RL has shone. RL in simulation and then sim to real with some new ideas. I mean, it includes like domain randomization, but I think this RMA idea is a good one, and so forth. We have kind of the recipes, we should be able to do it. Okay, let's talk about manipulation. So, and in particular, this connects to one of the principles from child development, multimodality. If you observe children, they are playing around with the environment in which they are. They take objects, they put them in their mouth, so they have got touch, they've got even taste maybe. They bang an object, so they get sound, they get vision information. So it's all of these modalities are operating together. And the beauty of this is that, of course, it's a richer signal, richer sensory signal for control, but it also enables training in the sense of, I won't have time to get into it, but cross-modal supervision is a beautiful way to train these various modalities. One of them can supervise the other, basically. Okay, but I'll illustrate with this paper, which is on doing the following problem: rotating an object in the hand. And this is, I think it's a beautiful problem because it's a dynamic problem. If it's not just quasi-static, and then it becomes challenging if you consider different axes of rotation. And how we did this was using both vision and touch. So we wanted generalization. To me, if you show a skill, it has to be generalized across different objects. So that's essential. So we have a camera looking at the object, and then it's getting some partial observation because you can't see the backside of the object. Plus, you have signal from the tactile information on the fingers. Okay, so it's a combination of the two. And here's the task. So the task is to rotate about different axes. So the top row is rotation about the x-axis. So you see the axes labeled in this the coordinate. The third row is the easy case, which is rotating about the z-axis. Okay, the top row is x-axis, and the second row is the y-axis. So let's see how it works. So again, one policy. Okay, well, it's different policies for the different axes, but I mean, you can distill them together. But the important point is it's generalized across all these shapes. It doesn't have prior knowledge of this. So what's happening is, in real time, from the visual data, from the tactile data, from the proprioception data, enough is being estimated about the object that enables you to do the right thing. Okay? So a little bit of what you do, you need to, the vision information, you have to sort of segment out the object, tactile information. Anyway, I won't go into the details. At high level, this is not that far off from the approach, the RMA style approach we used for locomotion. Okay, by this time we were using transformers like everybody else. But there is this variable z which you can see, and that's capturing somehow this latent state. And but if you look at the upper left, the key things here is that you use privileged information in training, so you know information about the shape of the object. But at runtime, you do not know the true shape of the object or its pose. You're estimating it from the vision data and the tactile data. Okay, this chart to me is the most important finding from that. Okay, yeah, so it worked, we showed the demo, fine, everybody's happy. But the biggest lesson from that was this one for us, which was, how is the performance? So the y-axis is performance, which is like how many rotations before it falls down, something like that. So if you have ground truth knowledge of the shape and pose of the object, that's the extreme right bar. Okay, so that's the best you do. On the extreme left is if you have no sensing, or rather you only have proprioception, which is the lowest performance. Then the second bar from the left is just using vision. The third bar is just using touch. Okay, so both are helpful. But vision and touch together is the fourth bar, and it's almost to what you get with ground truth knowledge. So what is the answer? That means that vision is helpful, touch is helpful, the two of them together, and of course, proprioception is always there, is almost as good as having ground truth knowledge. This is a fundamental insight which I think should guide all of our work on manipulation. Because if you show me a result that you can do the task with vision, I'm actually not impressed, even though I'm a vision person. Because, yeah, it'll work, but maybe it'll work at 85% level, right? I want, eventually, if we want our robots to be useful, we have to strive for the 99.999 kind of percentage. And at that point, it is foolish to not make use of full sensory information. We have these hands for a reason. God did not evolve us with parallel jaw grippers, okay? They gave us multi-fingered hands, and those multi-fingered hands have tactile sensing in them. For Christ's sake, use them, okay? Okay, in that spirit, okay, so this is a paper from a team at Meta, and I want to particularly acknowledge the first author, Mike Lambetta, who hopefully is somewhere in the room in case there are some questions that I get asked, which I need to ask him. And then and Roberto Calandra, and this is a big team. But this is basically this Digit 360, which is a very fancy sensor. It has spatial resolution. This paper is out on archive, so you can read it. But it's an attempt to go after what the beauty of the human skin and the tactile system. I have this photo on the right. We have these so-called Merkel receptors, the Meissner corpuscles, Pacinian corpuscles, and so on. These are all things that the neuroscientists have found, and they have varying sort of spatial receptor fields, low-res, high-res, varying temporal stuff. There are pain receptors, temperature receptors, et cetera, et cetera. So what you see on the left in this Digit 360 is an attempt to build in these various multimodal sensing capabilities in the sensor. Okay, so and then we can do amazing things with this. So here are some examples, and again, you should read the paper. So for example, you have a glass, and you want to know whether it's half empty or it's full or empty, right? You can judge that from the way you lift it, and if you shake it, the sound, et cetera, et cetera. Similarly, at the bottom, there's some example of tactile sensing of some material. On the right, there's an example for an egg. Is it a cooked egg or is it a raw egg? These are all capabilities you have with the richness of tactile sensing. Okay, so then why are we all not using it? Why are you all not using it? I think the answer is clear. I mean, dealing with multi-fingered hands is a pain. Dealing with tactile sensing is a pain. It's not as easy as working with a parallel jaw gripper or working with vision. I mean, vision, everybody in the world has a camera, right? So we are trying to make life easier. So this is, when I say we here, I mean Meta. And so basically in collaboration with GelSight, there will be manufacture and distribution of Digit 360. We are going to have a mechanism by which academic groups can apply and get this. And then there's a deal with Vonik Robotics. These are the makers of Allegro, where the hand will be equipped with tactile sensing. So what I'm trying to do is, okay, I'm trying to do this sales pitch here, which is, please, please use multi-fingered hands with tactile sensing. The more people get into this, the closer we are likely to achieve success at dexterous manipulation. Before that, you can show clever little things you can do with parallel jaw grippers, but fine, okay? I'm sure there are settings in which those are needed, like, I mean, you're doing some laparoscopic surgery. I mean, surgeons are amazing with those tools. But long-term future, I'll make an analogy here. In computer vision, we can recognize faces in 32 by 32 pixel black and white images, or even 16 by 16 for really famous people. But do you want to spend your life with all the images you see being 16 by 16 black and white images? I hope the answer is no. You want color images, you want 1,000 by 1,000 pixels, you want video. Use it, okay? Use multi-fingered hands, use tactile sensing. Okay, and this is an announcement of how you can get into the action. Okay, so let's keep moving. So I want to, so this is a paper which was presented earlier at this conference, but it's in this paradigm. So of course, in my group, we do a lot of stuff with reinforcement learning and sim-to-real paradigm. And this is an example of this task, which is twisting. So you have a bottle and you want to twist the lid off, and it has to generalize over many different bottles. And here are some results. And then if I let it continue for long enough, eventually the bottle cap will fall off, and that's the success. And the important point here is generalization across different objects. Okay. I could keep going, and at some point you want to say, okay, is there a pattern here? Is this just like another day, another paper, or another 6 months, another PhD student, another paper? There needs to be some template to this, some organization, so that we feel, okay, on this path, we will eventually solve the problem. Are we merely building taller ladders to get to the moon, or are we building airplanes, or are we building rocket ships, right? We need to do that. So for me, this was one insight which goes back to actually a paper we did with colleagues at Google and with Cordelia, who's here. If she remembers this. It's AVA, Atomic Visual Actions. So we were trying to solve a vision problem, understand video. And if you look at video for any extended period, it's infinitely many possibilities. So just like there are infinitely many sentences, there are infinitely many actions that people can be doing. Like there can be birthday parties, there can be, whatever, right? Okay, but suppose you limit yourself to 1 second. Over the scale of 1 second, and you look, what's happening is a physical action. And it turns out that we basically made up this limited list of 80 categories, which includes pose change, so like walking, running, etc., interactions between person and person, person and object. And we did the following experiment. We gave this to annotators who had the choice to mark none of the above. And essentially, looking at many, many hours of video, they could mark 95% of the frames this way. So that means that it's not like there's always a tail, but you get like something like 95% coverage out of these 80 activities. Okay, now let's flip this around. So basically, a new insight is, this is how we observe action, but then somebody is doing the action, and let's say now we have a robot which wants to do the action. Now, maybe we're not all of these. I don't know if we need our robots to be kissing each other or us, okay? But a lot of, for example, the person-object interaction, I mean, that might be something we want to do. So with that perspective, we said, okay, let's see if we can make a list of common atomic manual actions. So this is, you see the spirit, atomic visual actions, atomic manual actions. So this is work with Housie. So we tried to find, if you look at like 100 days of hands, what are the common actions? So think of the time scale as 1 second. Over a longer time scale, there are infinitely many possibilities. Over a time scale of 1 second, there are certain actions which get repeated all the time. And so this is a list. Don't think of this as holy. This is like 20, maybe it's 50, but it's not 1,000. I think of it like phonemes, right? I mean, phonemes are on the order of 50. We start out with a bigger repertoire, and then it's fine-tuned to our language. So, of course, when I say use the term insert, I mean this as generalizing across different object categories, right? So these are all examples of insertion. So, but this is what we are used to in vision, right? We talk about category variation. All cats are not identically the same shape, right? And they have different poses and different lighting conditions. So these are variations on insert. These are variations on cut, right? You're cutting with a knife, but you're cutting different objects, okay? And now it may turn out that you need different mechanisms for some of these subcategories, but okay, that's open. We are just defining the problem. And so here are the set of atomic actions which don't involve the use of tools. So they include the usual things like opening drawers and pick up and put down in a dishwasher, pushing an object, inserting, pouring, things like that. Here are some which involve the use of tools. So stirring, cutting, writing, wiping surface, and so on. So so where do we go? So each of these, I can use the term action, but maybe let's use the term skill. So these are atomic skills, and I'm arguing that that number is small. Maybe 20, maybe 50. On this order, and of course, once you've learned 50, 51st one should be easier to. So this could be a target for the robotics community. Develop robots that can demonstrate all these skills. And initially, it will be like you'll be doing case by case. In computer vision in the 1990s, we used to do, you could get a PhD for just doing face detection, right? Another PhD for doing OCR. But eventually, we developed general techniques. So we want general techniques. Now, we have general techniques today, right? We have reinforcement learning. We have supervised learning with teleop for collecting trajectories. We have visual imitation. There can be combination of the above. But to me, the proof of the pudding is how many of these skills can you demonstrate with your robot hardware? Okay. I think that this subsumes the task of locomotion because those are certain skills. Manipulation are skills which involve person and object. Okay. So I talked enough about the use of reinforcement learning and supervised learning is with teleop is, of course, very popular these days, but I don't want to say more on that. But let me focus on visual imitation. So here is a paper from colleagues at Berkeley and Anju Kanazawa and me. We were kind of playing the role of the vision people in this robot vision collaboration, which is how to make this Atlas do cartwheels. And it's a reinforcement learning problem. It has to be done in a physics simulator. But you want to have dense rewards. So the way you can have dense rewards is you take this video of a human, you download it from YouTube, you extract the 3D pose of the person in every frame, and then that becomes the target for pose for the robot. Something like that, right? So we call this skills from video. And importance of imitation learning has been recognized. So there are variations of, the term imitation learning is unfortunately used in many different ways. For some, it actually just means, teleop trajectories is also a kind of imitation. When I say imitation, I mean visual imitation. So when a child observes a parent do something, okay, and then has to learn from that. And in the setting that I want this to be a solution to the big data problem. So basically, we have YouTube. YouTube has like 156 million hours as of a few years ago. So you should have the ability to download a video, do some stuff, okay, and use it for training your skills. It won't be just that, because this data misses some essential things, right? Because you have to make some inferences here, because you can know the joint angles and so on. There is, but you are missing kind of the mental state of the person. You don't know what actions they intended. So there is some missing information. But in learning, there are ways of dealing with missing information. So right, the intended action you don't know, but you can consider that missing. You may not know what is that person perceiving, because they might be reacting to what's in their visual field, and you may not know that. So with all those caveats, this is going to be noisy data, it's going to be incomplete data, but the beauty of it is that it is huge. And you don't have to pay people, whatever, $20 an hour or whatever to collect it. I mean, it's there. You just have to download it. And I believe that this is going to be one ingredient of success. I'm not trying to argue that this is the only way, because it's incomplete in some ways. So, and if you think about children are doing a lot of learning by observation, like this. And then they're doing some which is in their own bodies. They are interacting. So maybe it's 90% observation and 10% interaction. But both components are important. Okay? So Okay, so first, so here's an example where we are applying it to locomotion. And we've gone through, we've written a series of papers on locomotion. These are all led by Ilya Radosovich, who's my PhD student. And this paper, which is going to come out at NeurIPS, we tried to essentially use the paradigm which language people use, right? Next token prediction. But here the tokens correspond to action. So we have to deal with the missing data problem, but you can do that. I mean, this, okay. And you get a data set of walking trajectories, and you get some which you can get from your RL-based learned controller. You can get some from your model-based controller, which the manufacturer of the robot can give you. But very importantly, you can get some from internet videos. So you have lots and lots of videos of people moving around, playing tennis, whatever. And now you have to solve the retargeting problem because the embodiment of the robot is not exactly the same. And then you got a trajectory. It's noisy, it's incomplete, but throw it in. I mean, one of the lessons of modern deep learning is just more is better, and even if it's incomplete or noisy, it washes out. And then again, I mean, this paper is on arXiv, and it will appear at NeurIPS, so you can read the details there. But we show that the addition of this data, it actually helps, and then the robot, I mean, these are results from that. And and then there are clear benefits. The resulting trajectories are smoother and so forth. So again, read the paper for the details. Okay, but I mean, we should also acknowledge one problem with imitation learning, right? The problem with imitation learning is what you see is all you will have, because you are reinforcement learning can be genuinely creative and come up with solutions that the designers have not thought of. With imitation learning, you're going to get some kind of smoothing and interpolation of the data you've collected, which is fine, but don't completely rely on that. So I think mixing and matching with these other techniques, so I think there are these three techniques, right? There's reinforcement learning, there is teleop demonstrations and supervised learning from that, and then there is visual imitation, which is this slightly incomplete information. In my mind, right now, all three are promising, and all three should be used in various combinations. They have pros and cons, but so anyway, so one thing we did here was that after we had this robot which was walking on flat ground very well and robustly, how do we get it to walk up on slopes? Okay, so now what you can do is you can take that model, just like the learning people do. You build a model first with tons of data, and then you fine-tune it like RLHF or whatever. So here the fine-tuning is done by, in a simulator, making it walk on various kinds of slopes. And then, of course, I live near San Francisco, which is the city with many, many hills. So here are demos which are walking on, so what you see in each of those panels are the slopes of the streets. And, but I will leave you with this. This is hard even for humans, okay? I mean, you try it. I mean, you know, okay. Okay. So the idea is that these various learning strategies for skills can be mixed and matched. Okay, now let me turn to imitation learning for robot manipulation. Again, I mean, this idea has been around for a while, but let me tell you the take that we have taken in my group. So I believe the successful path to this goes through 3Dification. Okay, it's also the case that as a computer vision person, I want to have some use of my computer vision skills. And 3D is like a classic problem in computer vision. We have worked on it for decades, and it still has some juice left, I think. So the goal here is you have some video, and I'm talking here of the setting where we are dealing with data which you just download from the web. I'm not talking about the setting where I collect data in the lab with cameras of you doing something. I mean, that can be done, but then I'm losing out on the advantage of, you know, the 156 million hours of video on YouTube. I want to work with found data, not data I'm collecting myself. And OK, so there was an earlier paper where we managed to make this work in some settings. But it needed CAD models or objects. So basically, I had to assign this as a homework problem for the students in the computer vision class, that for each video clip, they had to find the right CAD model on the web. OK, this was not a scalable solution. If it needs Berkeley grad students to solve the problem, it's probably not the right way. OK, but this is more recent work, and I'll show you. Again, I won't get into the details, but let me show you a demo where what you'll see are video clips where both the hand and the object are now in 3D. And then, of course, there's a task of using them for robotics. So you see the hand in gray and the object. So it's a 3D model, as you can see from the side. And sometimes you'll see problems like the hand is not touching exactly right and so on. But my belief is slightly noisy data is OK. So these are all video clips where you have detected and tracked the hand and lifted it to 3D, hand and the object to 3D. And you'll see problems. Sometimes it doesn't touch correctly. Sometimes there's an intersection. But trust me, the computer vision community will solve this. OK? And you will have somewhat noisy solutions to begin with, but start using them, because this is big data sitting on your doorsteps or available from YouTube, right? OK, here are some examples which do for one frame, and these are trying to show the 3D reconstructions by spinning around the object. So, OK, so here are some examples, other examples. So I'm quite bullish on this. We've been trying to do this for years. It's a hard problem. It's not fully solved. I think the hand part of it, we have actually solved. If you read this paper called Hammer, it was presented at CVPI. You can download the software. It does a very good job of reconstructing the hands in 3D, even from a single image. The object part is the hard part, because the object is mostly occluded. You just see a few pixels. You try to do structure from motion. There won't be enough feature points, blah, blah, blah. I mean, vision people will understand how challenging the problem is. But we live in a world where we have a lot of data. We have CAD models. We have pretty powerful foundation models. I hate to use that word, but there are models which have been pre-trained with a lot of data. Let's call them that. OK? And we should use them. And I think, anyway, I'm just doing the sales pitch that you should use this. OK, what next? So this is like kind of nearing my conclusion slide. So I'm basically arguing that the central problem of robotics should be skills. So focus on skills, and a target is, can we get robot dexterity at the level of a 5-year-old? OK, or if you're more ambitious, a star athlete, or a proficient mechanic, or a chef, right? And then, but of course, skills are the lowest level, right? 1 second unit, right? We want to solve tasks. We want to achieve tasks. So then we have to do compositionality. So I'm totally on board with the philosophy that Tomás Lozano Pérez articulated in his talk. I think we differ about what the units are. For me, the units are skills, because each of them is a controller. So it is sensing and acting. So it's a control loop, which gives it a certain robustness. And I want to make those as the building blocks. And then they can be composed. Now, how do you do a new task? You will compose some set of skills. So my canonical example is how to learn to play tennis. So I don't know how to play tennis. I go to the tennis court. I will be able to zero shot, throw a ball, hit it with a racket, get it to the other side. Hopefully it lands in the right place. OK, but I'm not Roger Federer at this point, right? But zero shot, I have composed the skills, and I can play legal tennis. And now I practice, right? And I practice. So conjoined skills over time, they gain proficiency and automaticity. And that's what athletic practice is about. And if you want to use Kahneman terminology, it starts out system 2. You are very deliberate. You're thinking through the steps. And after a while, it just becomes like a routine. Driving is like that. When a kid at 16 takes driving lessons, they have to be very conscious. And after a while, it sort of becomes a routine or a skill. So we have a huge repertoire of skills. It's not just those 50. But those 50 are the atomic skills from which to start this bootstrapping. And kids are learning them. So from the age, from 0 to 3, 0 to 5, 0 to 7, what a kid is doing, if you observe them, and I have colleagues who are child psychologists who do this, that's what they're doing. Okay. And I'll conclude with this example, which is you can have a hierarchy on top of a skill. So this is a paper with Andrea, Antonio, Ashish, and, which was presented at ICRA. And I'll just show you the task. So this is the task, which is it's like a pursuit evasion game. Or if you want to be friendly, it's like you're playing hide and seek. And this robot dog is chasing after her. And it does this well. But what did we do? We took the basic walking skill. So we take as a given the ability of the quadruped to walk in a particular direction, which we have trained earlier. So that was a basic skill. And now this is a skill on top, which is, find her. And it turns out, and you can train this with RL in simulation, and then use it in the real world zero shot. And there are behaviors that emerge. For example, you don't want to go to where the person is now. You want to go to where the person will be. You want to have some kind of observing behavior. If you don't see the person, you want to look around and so on. All of that emerges using reinforcement learning. So this is an example of hierarchy, right? You have a low-level skill, which is the walking skill. And then on top of it, you build the seeking skill, and so forth. So to me, all of human activity and behavior is just skills composed with other skills built up on top of other skills with a layer of planning. And one day we will solve it. And otherwise, thank you.
So we have time for a few questions. In the back.
Hello, thanks for the really inspiring talk. It seems like there's a gap between hierarchical control and end-to-end control. It seems like human beings, firstly, when we learn some skills, we do it hierarchically, and by training, become end-to-end. I don't know, how do we do it in computer science and robotics to build this process?
Yeah, so to me, hierarchical control or planning is one of the great challenges. So hierarchies emerging automatically is what we would love, but I don't think right now we have good techniques for that. So in control, often these hierarchies are imposed by design, and we did the same, right? We decided that this could be done with 2 layers, where one layer is walking, and then we were doing the layer on top. So for now, design is a reasonable way to proceed. Long term, I think with the creativity of people, we will find some way where more of it can be made automatic. But in the near future, I think of it as design. I'm not buying the story that all of motor control can be done by end-to-end training for particular tasks. I think that's not going to work. So imagine, okay, so my problem day after tomorrow is I need to go from here to San Francisco, right? So I'm going to walk, I'll take a taxi, I'll get on a plane, and so forth. Is this the problem that you can solve with end-to-end training? I mean, this is nuts, right? You have to break it down into tasks, into subtasks, and so forth. So those classical ideas of planning are quite relevant. But the lower levels are, I think, where you need control loops for where learning plays a very major role.
Wait, question?
Yeah, beautiful talk. I need time to digest, but I have 2 high-level questions. So you argued that we need 10,000 less data, but you didn't tell us how we should get there. I didn't get how we should do there. And my second question is that, so atomic skills is, I think it's the way to go, but you said newer skills, now it's easier to learn, but we never leverage the data or the knowledge we gained from the previous skills to the new ones, because we do deep reinforcement learning, and we sit there, tune for each single task without transferring knowledge. So I wanted to know about your take on these two.
No, I think your question is spot on, and my answer is I don't know either, okay? What I'm claiming is that humans have both these capabilities. So for language learning, they manage with 10,000 times less data. So therefore, there must be a way. That's an existence proof. And I am trying to do this in the context of motor control. I'm not so interested in the language learning task. And that's why I'm looking at all the insights that I can get from the psychology literature. And I made up a list of some of that, and this is a direction to pursue, but I do not have the answer. And the same is true for your second question, which is that from the 50th skill to the 51st should be easier, but I do not have that answer either. Yeah.
Okay, next question.
Oh, hello. Yeah, thanks for the talk. So regarding the part that you discussed where people are able to look at a video and classify like human-object interactions into, say, 50 or so primitives, to me that seems to be more of an artifact of like language being able to classify human behaviors into certain categories, right? These are the things that we care about communicating, not necessarily like the lowest level control primitives that you would want to be composing or reasoning about. So can you expand a bit more about why you believe that like that level of abstraction is where we should be doing our planning? Because so many of those things seem so highly contextual.
Okay,
right.
Good question. Okay, essentially you made an assertion here which I don't fully buy. You are saying that categories follow language. I'm saying language follows categories. I'm basically making the assertion that it's the other way around. And primates, I mean, apes, monkeys, they have categories. I have colleagues who train them on these classification tasks. Jim DiCarlo at MIT is one of those people. And basically, these macaques are amazing at it. So they understand, they get category structure, actually most animals have and they need, okay? I would say language builds on top of that, because if you have a category, then you can make a symbol for it, and that's your word in language. So that's one point. You have made a second point where I think I'm in partial agreement with you, which is the point that physical actions are on a continuum. So at some sense, joint angles are in like some 50-dimensional space or whatever, and I'm quantizing it. Fine. I think it's okay. There are quantizations which exist. For example, for walking versus running. It turns out that there are these two clusters, and they make sense, and there's some energetic story associated with it. So, I mean, you think about phonemes, right? So, I mean, the articulatory apparatus of the tongue and the lips and the throat and so forth, I mean, again, it's like muscles. So therefore, that's also on a continuum. But then we use it in ways where these clusters occur, and we call them symbols. But that there is an underlying continuous space is good, right? Because the language people found that the way they made progress in language was by going sub-symbolic. Classical linguistics was all about symbols, which were arbitrary and had no meaning in themselves. But now what do we have? We have these 300-dimensional embedding vectors. So the beauty is that for us, that is already there. The physical action is this, whatever joint angle space or the space of the rotation and translation of the object. So there should be an underlying continuous space, R100, whatever, and then there are these symbols. And the beauty is in the interplay of these ideas. And we don't understand that yet fully. But I'm just, I mean, I see a lot of a veil of darkness, but at least I see a path.
I see. I do think that you also sort of made the assertion back at me that like language were built off off of categories. I don't think that I think that a lot of linguists believe that these categories are not necessarily natural, right? The ones that become things in language are heavily shaped on the values and practices of a given culture. And so are these necessarily the instantiations of skills that would be optimal for robot control?
No, that I'll grant. I mean, what you said just now, I agree with. I mean, language is not, so language starts out in physical grounding. So if you consider the language of a 3-year-old or a 2-year-old, a lot of it is related to the physical world. And there are experiments on that. The words that they have in their vocabulary are very tangible, and they can perceive them, they can imagine them as motor programs. As they get older, they learn about concepts like justice, faith, hope, charity, and so on. Okay, those are much more abstracted, and I should not think about grounding them in motor acts. But that is happening then where it's language qua language, and it's the relationship of words to each other. So then it feels very much like how GPT-4 is being trained. But there is an initial grounding which is in the sensory motor world, the perceptual world and the motor world.
All right.
Okay, we'll have one last question in the interest of time.
Okay. Thanks for all the insights in the talk. I think today's discussion is pretty policy and controller-oriented. I want to ask the part missing in the talk is a predictive model of the future. How would you think about a world model of the environment to be part of the future robots, in the robotics?
I mean, this is implicit in what I said, because world model is a new term, but control theory people have known about dynamics forever. So, I mean, if you read your Kalman paper or whatever, right? The standard framing x dot equals ax plus bu. What is that? That's a model of the dynamics of the system where x is the state vector and u is a control variable. Okay, now you can make that nonlinear where you make it like f of x comma u, etc. Right? I mean, the control theory is based on this idea that there's a model of the dynamics which comes from the fact that these are physical objects and Newtonian mechanics applies. Now, we can extend this idea of dynamics to other settings, including human behavior and so on. Actually, Pulkit and I had a paper on it ages ago. So, yes, we do need dynamics models. I mean, that's my term, but you can use the term world model if you like. And these are, and this is what control theory people know. I mean, that's how you design control laws. Now, you can be explicit about it or implicit. And that to me is like, I'm okay either way. Okay, I think that, I do think there is a value to having models if you can acquire them. Sometimes we can acquire the policy without the models. And I mean, this is a standard topic which has been, I have nothing new to add there. But I want to add the following. World models is really the idea from control theory.
Okay, thank you for your answer.
Yeah.
Great. So it's 15 minutes into lunch and we are still glued. So that means it's an exciting discussion which will continue in the keynote panel, which is slated for afternoon. So please come with your questions. And with that, let's thank the speaker once again.